I've mentioned a couple times in this course that a lot of the rocks and polished stone that people call granite are not granite in the geologic sense. In fact, a lot of metamorphic rocks are called granite, even though granite is igneous, not metamorphic. Take a look at a polished rock that the dimension stone industry has called granite. Often the so-called granite will have patterns in the colors or vague linear accumulations of the same type of mineral, or even stripes or lines. But if you see any of those patterns, you are not looking at a granite. What you are looking at is a metamorphic rock. See this sample? Can you see the middle pink section and the dark zone on either side? Or this sample, do you see the orientation of the reddish minerals? Look for how the white minerals are separated from the dark ones in the pattern. Frequently, you might be looking at a rock that was once a granite, but has undergone a change in chemistry or mineralogy called metamorphism. Each of these samples was originally a granite until they underwent metamorphism, which created the patterns you can see. Metamorphic rocks are rocks that have been changed from one state to another, whether by the effects of heat and or pressure and or fluids. The process is called metamorphism, from the Greek word meta, meaning change, and morph, meaning form. So, change of form. Metamorphism is an amazing process that can result in amazing products. Frequently, metamorphic processes result in either an economically valuable rock or in an economically valuable mineral within the rock. Metamorphic rocks most commonly form under conditions intermediate between those for sedimentary rocks and igneous rocks. You remember that there is a geothermal gradient, right? For Earth's crust, this is where the temperature increases roughly 25 degrees Celsius or 45 degrees Fahrenheit for each kilometer below the surface of the Earth. Well, near the surface of the Earth, new rocks form when relatively low temperature and pressure bring sediments together to form sedimentary rock. Alternatively, deep within the Earth, under the highest temperatures and pressures, conditions are so hot that all rock material is completely melted, resulting in the formation of igneous rocks. Metamorphic rocks form at a variety of intermediate depths under a variety of intermediate pressures. What are intermediate temperatures and pressures? Conditions that allow for brittle rock to become ductile, yet not hot enough to melt. This is why metamorphic rocks always form from pre-existing rocks. Metamorphic rocks always metamorphose some other rock. And this is why every metamorphic rock has what is referred to as a parent rock or protolith. It doesn't matter if the parent rocks are igneous, sedimentary, or even another metamorphic rock. What happens is that the parent rocks are altered because of heat, some kind of unequal stress, or interaction with fluids. Remember last lesson when I mentioned that some igneous minerals recrystallize in a solid state? What's interesting about metamorphic rocks is that all metamorphism occurs as a solid state transition at temperatures where rock has become softer yet does not melt. And because these are solid state changes, frequently the overall chemistry of the rock does not change at all. For example, this granite gneiss would have formed from a parent rock like this pink granite. And what you have are minerals changing size, as in this sample, where these large pink crystals of feldspar probably looked like these small pink crystals of feldspar in this parent rock. You also get some minerals changing to different minerals without the overall rock chemistry changing. At a depth of 8 kilometers, the temperature is hot enough for some new minerals, such as the mineral muscovite, to form within an existing rock. Meanwhile, other parent minerals, such as quartz or feldspar, remain unchanged. It's only when you add hot water to the system that the overall rock chemistry changes. With water present, dissolved ions will pass in and out of the rock, changing the overall composition. Once water is added, you have an open system in terms of chemistry, and all types of interesting metamorphic rocks can form. Metamorphic rocks are divided into two groups. Some metamorphic rocks, like slate, have a linear element that results from preferred orientation of minerals. Metamorphic rocks with patterns are called foliated. When a foliated rock is subject to metamorphic forces that are more intense, two other types of pattern rock result, called schist and gneiss. By contrast, there are also metamorphic rocks, like marble, which are very homogeneous. Such rocks do not have a preferred orientation of crystals, so they are called non-foliated. Quartzite is another example of a metamorphic rock that's homogeneous. It forms when sedimentary rock quartz changes into a metamorphic rock called quartzite. Marble and quartzite look fundamentally different from the patterns of slate, schist, and gneiss. The difference is that rocks like slate, schist, and gneiss have patterns we describe as foliated, while marble and quartzite are unfoliated. We'll look at the more subtle characteristics of non-foliated rocks, like marble, in the next lesson. For now, let's consider why are foliated rocks foliated. Foliation results from mineral growth perpendicular to stress. Let's see what that means, mineral growth perpendicular to stress. Imagine you're squeezing a ball of modeling clay. The clay flows perpendicular to the stress. In geology, this stress is called directed pressure. Similarly, in metamorphism, the rock is still in a solid state, so the mineral growth or reorientation occurs in a similar way, perpendicular to stress. So foliated minerals are changed in one of three ways. Rotated, so they are aligned into a parallel arrangement, or they recrystallize in a preferred orientation, or the shape is changed. For example, a spherical grain under pressure becomes elongate. This is something we talked about in the lesson about glaciers. Glacial ice is a metamorphic rock. And while it's odd to think of any kind of ice as a metamorphic rock, glacial ice is actually a great example of metamorphism. The sediment, in this case, is snow, which under pressure grows into interlocking glacial ice called firn. During this metamorphism from snow and firn to glacial ice, the crystals can undergo three changes. The crystals are rotated, they recrystallize, or undergo a shape change. But in metamorphic rocks, not all foliation develops perpendicular to stress. Foliation can also develop when minerals have been smeared out parallel to stress. This is called shear. Imagine if you put a ball of clay between your two hands and try to slide the two hands past one another. The clay will be sheared, and a result will be to leave behind patterns that are aligned in the direction that your hands were moving. Okay, let's look at the four most common types of foliated metamorphic rocks. Starting with slate. Slate contains minerals that are microscopic. As a result, slate looks a lot like the sedimentary rock shale. Shale is deposited in layers or strata. Slate is foliated. In fact, slate frequently forms from the metamorphism of shale. In these cases, shale is considered the parent rock or protolith of slate. But slate can also be formed from the metamorphism of mudstone or siltstone, or even volcanic ash as the parent rock, sometimes resulting in different colors. Slate is formed under low temperatures and fairly low to moderate pressures, so it is considered a low-grade metamorphic rock. Under pressure, The clays in the protolith are compressed until water is squeezed out and the rock is compacted. But the grains also begin to reorient themselves in response to the pressure. And bedding from the sedimentary protolith, as well as any fossils in the sedimentary rock, are likely to be compressed beyond recognition. So metamorphism has created a distinctly metamorphic structure. And it's this new metamorphic structure, which is oriented perpendicular to pressure, that's the foliation. This is clay. Clay metamorphoses into minerals of the mica group. Do you remember those? They had that cleavage plane. What happens is that the mica is oriented perpendicular to pressure. The mica is also compacted, and so you generate a very recognizable breakage plane called the cleavage plane. No other rock breaks in the distinctive way that slate does due to the pressure of metamorphism, the broad and flat cleavage planes of the mica minerals inside, and their parallel orientation with one another. The term slaty cleavage is used to describe this diagnostic characteristic of slate. Slate is familiar in everyday life. Slate was used to make the original classroom blackboards in the 19th century. By the way, 20th century blackboards were more likely to be surfaces covered with a dark porcelain paint rather than slate. Carefully quarried slabs of slate, like this one, are used to make slate roofs and slate flooring. The slabs are broken along very distinctive cleavage planes. Because slate is fireproof, it's also used as decorative stone around fireplaces. More recently, slate has been used as an upscale serving platter. You can warm it or cool it, and it will keep its temperature for a while. But an important note, do not put slate in a microwave. Yes, slate is fireproof, but the problem is that residual water is trapped in the pores. And whenever the water is heated to the boiling point, expansion of the water molecules will burst the slate apart. Slate is also used in very high quality pool tables. A single slab of slate can be polished into a durable flat surface as the bed of the table and then covered with felt. Because the level slate surface never warps, these are considered the best pool tables. But a single slab pool table is really heavy. Think 500 pounds just for the slate alone. So don't ever get talked into moving one for a friend. They're brutal, I've done it. This is why some slate tables come in 3 pieces, but then you need a professional installer to join the 3 pieces together. Similarly, a slate roof might weigh 4 times as much as an asphalt roof. Much of the world's slate is found in old mountain chains that are Precambrian or early Cambrian in origin, so over 500 million years old. In North America, slate is common along the old Appalachian mountain belt. Quarries were worked in Virginia, Pennsylvania, New York, Vermont, and Quebec. Other quarries were active in North Wales, Scotland, and Italy. And they all produced different colors of slate, depending on what was a secondary component of the clay parent material. During metamorphism, slate develops in different colors. If there were organics trapped in the clays, the slate will be black. If there was iron in the clays, the slate will be reddish or purple. A shiny slate has a lot of mica in it. The Pennsylvania slate is very high quality, but even though there is a great deal of demand, the production of slate in the U.S. is on the wane. In northeastern Pennsylvania, which produces a gray-black color slate, like the one I showed you, there used to be hundreds of slate beds that were being quarried. By 2020, there were just 2 or 3 economically viable beds. Another problem is the care required to cut slate. Slate cutting is an age-old process that really hasn't changed much over time. The slate is cut along cleavages in a typical quarry. This is the extraction process, and heavy equipment can be utilized. The extracted slabs are then cut with diamond-tipped blades. After the slabs are cut, the slate manufacturing process takes a step back in time. Slate is split by hand using mallet and chisels, the same tools that have been used for centuries. Once the slate is split, the final stage is trimming to size, and this can be done with machines. Roofing slate sometimes has nail holes punched in one end, like here. But this is tricky since driving a nail in the wrong place can split the piece of slate. So the process is time-consuming and requires a great deal of precision. Additionally, the amount of waste rock produced is both an economic and environmental liability. When slate was mined by hand, 1 ton of saleable slate would result in the production of 30 tons of waste, meaning that almost 97% of the process was waste. With modern methods, between 50 and 80% of the rock that is quarried for slate becomes waste product. I used to drive through the slate quarry region north of Bethlehem, Pennsylvania, and you could see the piles of waste slate from miles away. The economics of natural stone industries are always the same. The finished product, whether it's pool tables or roofing materials, often become too expensive, at least when you factor in the cost of the time and energy needed to yield such a small amount of finished product. Phyllite is another foliated metamorphic rock. It is also fine-grained and a lot like slate. Frequently, it has the same protolith, shale, mudstone, or siltstone. In fact, it is often a tough call to say one thing is slate and the other is phyllite. Phyllite is more tightly compressed, so it does not split into layers as easily as slate. But it does split, and it is also sometimes used for roofing tiles. Here's another example. The difference usually lies in the sheen that occurs in phyllites. Phyllites form under higher pressures, so the micas have more time to grow larger, although the individual crystals are not large enough to see. When this happens, the mica crystals merge, creating shiny surfaces, which is referred to as phylitic luster. These surfaces are frequently wavy. Another difference is noticeable when you're looking at phyllite in the field. Slate weathers to what are called tombstones. These are sharp slate slabs sticking up from the ground, like along Highway 49 in California. Tombstones of phyllite, on the other hand, are rare. The wavy surfaces and the easily weathered micas result in fairly rapid weathering, and this results in rounded outcrops. Schist is the next higher grade foliated metamorphic rock. It has the same shale parent rock or protolith as slate, and it has the same mineralogy. But because schist has undergone intermediate to high grade metamorphism, the minerals are substantially larger, and you can easily recognize them. Schists contain a number of different minerals. These typically include some quartz and feldspar, but there are others. The presence of these other minerals is used to describe and name the schists you're seeing, such as a garnet schist, a biotite schist, a muscovite schist, or amphibolite schist. If basalt is involved in the parent material of a schist, the resulting metamorphic rock can contain talc or graphite. Graphite, of course, is the mineral used for pencil lead, but it's graphite's unique thermal properties that make it invaluable in steelmaking, brake linings, and lubricants. The U.S. used to produce graphite in the late 1800s. Several companies mined a graphite quartz schist in upstate New York. This included Dixon Ticonderoga, the company which is famous for introducing the classic yellow No. 2 pencil in 1913. They are still making pencils, and students are still using them on standardized tests. But the company is no longer mining graphite. The last U.S. graphite mine, which was in Montana, stopped production in the early 1990s. Graphite has seen increasing uses in batteries. Think Tesla, whose lithium-ion batteries can use as much graphite as lithium. So U.S. dependence on graphite imports could be a problem in the future. Frequently, you also get schists with one type of mineral that has formed large crystals, at least crystals that are much larger than the rest. The garnets in this schist are a good example. These amphibole crystals in this sample are another good example. These large crystals are called porphyroblasts. They can be the source of gemstones, such as garnet, sapphire, or ruby. The problem with mining porphyroblasts, however, is that it's just too difficult to mine the rock if the gemstones are small. In the case of sapphire and ruby, which are crystal forms of corundum, the world's second hardest mineral, weathering, the breakdown of rock in place, separates the crystal from the rock. That way, gems are mined in stream deposits. New York City, especially south of 110th Street, is underlain by what is called the Manhattan schist. It dates from the late Precambrian to the early Cambrian age, and it's a medium to coarse-grained schist. It is composed of biotite, muscovite, quartz, and plagioclase. The Manhattan schist is important because it is fairly resistant to weathering. As a result, when it shows up near the land surface, it creates construction challenges. There is an old myth that very tall buildings in New York could only be built right into bedrock. That myth arose because if you look at New York City, historically, there were clusters of tall buildings in the Midtown and down in the financial district. That's where the schist is near the surface. By contrast, down in Greenwich Village, where there were traditionally smaller buildings, the schist is buried 100 feet deep by glacial deposits. But New York architects can indeed build tall buildings in all parts of the city. So, the end of the myth. If you get the chance, you should check it out. There are exposures of the Manhattan schist throughout the city, but Central Park is a good place to look. On a sunny day, you'll see the sunlight sparkle off the mica in the outcrops. Other places to see classic schists, they're very common around mountain ranges. Think about when we talked about sediments early in the course. Shales are deposited in deep water along plate boundaries, so during tectonic events, the shales are frequently metamorphosed into schist. So schists, similar in both mineral composition and age to the Manhattan schist, occur throughout the Piedmont province at the foot of the Appalachian Mountains. So schists occur from Georgia to western Connecticut. Also, driving up into the Rockies from Denver, you'll see schist. A great example is the Great Pillars in the Black Canyon of the Gunnison. The last foliated metamorphic rock we'll look at is gneiss, spelled G-N-E-I-S-S, but pronounced nice, setting up all geology students for a series of terrible puns. The word gneiss is from an old German word for spark, probably because the rock glitters. Gneiss is a high-grade metamorphic rock. It can form from a sedimentary protolith, such as a sandstone or a shale, similar to how slate, phyllite, and schist form. Or it can form from an igneous protolith, such as granite. But what is different about gneiss is that the layers do not indicate cleavage planes, like those we saw in slate and schist. That's because the foliation of gneiss forms in a completely different way. During high-grade metamorphism, solid-state recrystallization occurs and the light and dark minerals are separated. What results is alternating layers of light quartz-rich zones and dark zones of magnesium and iron with dark mica, amphibole, and pyroxene. The separation of minerals is called banding, and it is diagnostic for gneisses. In North America, gneiss is found in the geologically older parts of the continent, from the Canadian Shield to Greenland. This is why gneiss has been mined for dimension stone in abundance in the upper Midwest. Architects often refer to granite gneiss rather than just granite. The gneissic banding is too distinctive to ignore. The St. Cloud granite gneiss was used for a portion of the Minnesota Capitol, a spectacular building. And this granite gneiss that I've been showing you comes from Milbank, South Dakota. It was used as an edifice component of the Petronas Towers in Malaysia, the tallest structure in the world when it was completed in 1998. So those are the common foliated rocks. But I want to talk a little bit more about foliation. We mentioned that metamorphism results from heat, pressure, and interaction with fluids. In order to generate foliation, the critical component is pressure, and specifically directed pressure. With directed pressure, a force is generated from a specific direction. Minerals will rotate, spherical grains will become oblong, and minerals will recrystallize in a direction that's perpendicular to maximum stress. So if we're looking at metamorphic transitions in rocks, and the chemistry doesn't change, then the differences can be attributed to changes in heat and pressure. That's where metamorphic rocks become so important to geologists. They provide a record of how much pressure a rock was placed under or how hot the rock got. This is called metamorphic grade. Metamorphic grade is defined by the degree of intensity of heat or pressure exerted on the rock. So high pressure or temperature rocks are considered high-grade metamorphic, and low pressure or temperature rocks are considered low-grade metamorphic. Metamorphic grade is determined by the degree of foliation, mineral or grain size, and finally, mineral type. What happens is that the rock, during the establishment of any given metamorphic grade, is establishing a mineral stability. As temperature and pressure increase, the stability of the atomic bonds is stressed, and the minerals will change to become stable under the new conditions. What sort of pressure makes foliated rocks? The big answer, tectonics. Two main types of metamorphism that generate foliation both result from motions driven by plate tectonics: regional metamorphism and dynamic metamorphism. Regional metamorphism results in a directed pressure that is the result of plate movements. Continent-continent collision at a convergent plate margin is a great example. A plate moves in a single direction, and as pressure and heat build during the collision process, metamorphic changes occur perpendicular to the direction of impact. The plate simply squeezes the rock. Directed pressure generated by regional metamorphism occurs over large regions. The eastern U.S., for example. Regional metamorphism results in a wide range of pressures and temperatures that can alter rocks. As you would suspect, the result of regional metamorphism is a wide variety of foliation and the foliated rocks produce. The progression is usually clay, a sediment, to shale, which is now a rock, to metamorphics, first slate, then phyllite, then schist, and then gneiss. The original rock chemistry remains the same, only the metamorphic grade changes through solid state transition and a lot of pressure. The second process that generates foliation, typically over a much smaller affected area, is dynamic or cataclysmic metamorphism. Dynamic metamorphism results from rock movement called slip along a fault zone. If this happened on or near the surface, the rocks would be brittle and would shatter and be ground into powder. But deeper in the Earth's crust, the same materials are more ductile. So during fault movement, as heat from friction and directed pressure from shear are both generated, the materials smear out in streaks. The result is foliation that develops parallel to shear, where the thickness of the metamorphosed rocks can range in size from less than an inch to over a mile. The rocks produced under these conditions are called mylonites. They have a stripy pattern that can look somewhat like gneiss. Again, the original rock chemistry remains the same. There's a third type of metamorphism that is far more unusual to find, at least on Earth. It's impact. This is also known as shock metamorphism. There are over 100 large impact structures that have been identified on Earth. Each of these structures was created by an extraterrestrial body, comet, asteroid, or meteors, hitting the Earth at high speeds. The metamorphic process that occurred during impact are incredible because they are exceedingly high pressures megabars, and high temperatures, up to 10,000 degrees Celsius. But just for an instant of time, the resulting rocks and minerals have features that are unique to this type of metamorphism. Planar deformation features, which are parallel planes of glassy material that form when shock waves pass through the underlying rock. High pressure minerals like stishovite and coesite, which are called shock quartz. Shatter cones, which are breccia created by the breakup of the impact site. Finally, glasses such as moldavite. This would have resulted from the melting of the rock, and it would have been ejected away from the impact site. What you're seeing is a glassy texture and a pretty green color that's been made into a necklace that I gave my wife. In the 1960s, people weren't convinced that many of the forms we now know to be impact features were in fact caused by impact. After all, Earth's surface processes eliminate crater landforms quickly. It was the recognition of the significance of shocked quartz that really carried the day. Geologists have conducted experiments to model impact metamorphism by putting quartz crystals on the nose of a bullet and shooting those quartz-tipped bullets out of a large gauge rifle into a slab of rock. They would then compare the artificially shocked quartz to the naturally occurring minerals. Those were the days of metamorphic experimentation. It's great to be a geologist. Foliated metamorphic rocks are important for their mineral content and for their use in commercial dimension stone. But for everyone interested in geology, they provide records of the past pressure and the past temperatures that altered them. It's these records that let geologists reconstruct ancient mountain ranges, plate boundaries, and faults that may or may not be visible now. They also provide a history of volcanoes and impact events otherwise long obscured by surface processes. And of course, foliated metamorphic rocks are beautiful to look at. They are a geologic marvel.